This is a fourth round of EPFL and RIKEN AIP joint seminar. Today, the speaker is Nicolas, and he's coming from EPFL. And so before we start the seminar, I would like to briefly introduce Nicolas. Nicola Flammario is a tenure-track assistant professor in computer science at EPFL. And before that, he was a postdoc fellow at UC Berkeley, hosted by Michael Jordan. And he received his PhD in 2017 from École Normale Supérieure in Paris, where he was advised by Alexander Aspromonte and Francis Bach. And his research focuses primarily on learning problems at the interface of machine learning, statistics, and optimization. And his research area covers a wide range of machine learning, such as optimization, robust learning, stochastic gradient descent, and sampling like gradient rangeband dynamics. So I believe that his talk will be very, very interesting. So I have been very looking forward to his work. So yeah, so please start.
Thank you so much. So hello, everyone. I'm Nicola Flammario. I'm an assistant professor at EPFL in IC. I'm reading the TML lab, so the lab about the theory of machine learning. And so it's really my great pleasure today to present you this recent work, which will be also presented at NeurIPS this year, about the implicit bias for stochastic gradient descent for diagonal linear networks. And this is a work done with my really amazing PhD student, Scott, and my not less amazing postdoc, Lucas. Okay, so they've really done most of the work. I'm only the messenger today, but I'm really happy to present you this work. And kind of have the paper, but if I have to tell you the story behind this work, it's really, it starts like a book for children, like once upon a time. So in fact, last year during the pandemic, Natis Rebro went on a sabbatical to EPFL to visit us. And then we had some meeting with other faculties working on the theory of machine learning. And we were brainstorming an open problem and interesting question to work on. And he really told us that for him, like one of very challenging and interesting open question of nowadays machine learning would be to explain the generalization difference of gradient descent and stochastic gradient descent. So in some sense, so it would be to be able to show that in some context, stochastic gradient descent can work in a better way than gradient descent. And that's something which was for me very, very unconventional, very weird in some sense, because I'm really coming from the convex world. And so I work a lot on stochastic gradient descent, but for me, always stochastic gradient descent was a way to save some time. It was like something computationally efficient, but the goal was always to try to be able to show that SGD was working as well as GD. But it was never, it was not like this fact that SGD can work better than GD and that the noise can help you to solve some problem was really groundbreaking. So we start to think a little bit about this. And and that's true when you look at in the related work, you have a lot of empirical work which are showing that when you are training neural network, stochastic gradient descent will often work better than gradient descent. So in the sense that if you want to use a very large batch, then it will be very difficult to find a solution which will generalize well. And so the generalization of a small batch SGD empirically will be often better than the one of large batch. So that is something which has been observed a lot in practice, but it has never really been theoretically proven. And more recently, you had some work who tried to investigate this fact theoretically, but in fact, they only focus on the case of label noise. So that means on the case where you are not exactly running the stochastic gradient descent algorithm you will run in practice, but you are adding some noise in the label. So in some sense, you are dumping the noise of your iteration, And in that case, you can prove some results. So you have like this recent work, which are very nice. Either they work directly on the implicit bias of SGD for general model, or they also focus on the same models than us, on diagonal linear model, but they are always considering not the actual stochastic gradient descent algorithm, but the one where you are adding some noise on the labels. So in the general case of SGD, there hasn't been so much work. And so this, really what I want to show you today, and that will be, like the plot, kind of, it will be the plot of the talk. It will be also the only plot I want you to remember. And that's really like the starting point of the project, and that was also the end point of the project. That is, it's possible to find a setting. Okay, everything will become clear in the next slides, but it's possible to find a setting, namely it will be a sparse regression problem, for which you can observe and you can show the generalization property of gradient descent and stochastic gradient descent will be different. And you see that the generalization property of stochastic gradient descent will be better. So using stochastic gradient descent, starting from the same point with the same step size, you will get an estimator which will generalize better than if you had used gradient descent. So that's really, like the first experiments I did on this project, and that really motivate, us to try to understand, is it possible to theoretically find an explanation for this curve? Okay, so this is what we will try to do today. So what is the setup? So the setup will be the classical setup of overparameterized machine learning. I will consider that I have n observation, x, y, yi. Xi, the input will be some vector of dimension d. The output y will be real. I am in the regression setting. I am supposing that my observations are IID according to some low rows that I don't know. And what I want to do is that I want to find a function fw of x in order to predict my output, okay, as it is classical machine learning. So like the aim is really to find the parameter w star, which will get me the best function f of w star, such that I will almost surely recover my output y. And so, for example, we can parameterize our model class using some linear model. This is the simplest case that you all know. So fw of x will be equal to w scalar x. I can also model my model class using a neural networks. Okay. And today we are really interested in the overparameterized setting, which means that d and the number of parameters will be really, really larger than the number of observations. Okay, so n is very large, d is very large, but d is really larger than n. That would be very important. And so you know that when the number of parameters is really larger than the number of observation, then it will exist a lot of different solutions which will perfectly fit your training data. There is no unicity of the interpolation. So when you will look at the minimization problem of minimizing your training loss, you will have a lot of different minimizers. And so the question is, imagine that you can minimize this training loss even if it is non-convex. Which minimum should you consider? Which minimum of the training loss should you pick, and how can you pick it? So that's, really like the motivation. I mean, what I already told you before is that we know that over-parameterized neural networks are generalizing very well when they are trained with stochastic gradient descent, even if you have a lot of different minimizers of your training loss, and that you are using very few regularization. And so why it is working so well? That's really because, in fact, your training algorithm, so either GD or SGD, has in some sense what is called an implicit bias. That means that your algorithm is not just selecting one solution of the training loss, one minimizer of the training loss, but your solution is picking one particular good solution which will have some good generalization property. Okay, so this is the very important concept of implicit bias we will talk about today. you have a lot of different solutions. Your algorithm, your optimization algorithm can pick any of them because it just wants to minimize your training loss. But in fact, you are picking one particular solution, and this way of selecting one solution, it is what is called the implicit bias. So this is like the same motivation, but with some pictures. You see that if you have some simple 1D data, so in the horizontal axis, you have the input X, in the vertical axis, you have the output Y, and you want to fit a model on this observation. If you are minimizing your square loss with any particular training algorithm, you see that you could find a lot of different interpolation curves. You could find, for example, this curve with some algorithm, and you can find some other curve. And you can imagine that that one, in some sense, will overfit too much to your data and will not generalize well, whereas this one will generalize well. And so what will happen, in fact, is that GD and HGD algorithm will not select any random interpolation curve, but we will select one very particular, and this is what is called the implicit bias. So the first question is really, can we define better what is this notion of implicit bias, implicit regularization? What does it mean that an algorithm chooses a solution? And what is the type of description of the solution are we looking for? Can we be a little bit more quantitative? So really, like, understanding the implicit bias for the usual algorithm is something which will be very fundamental to understand why neural networks are generalizing well. So what do we mean by that? We have this minimization problem. I want to minimize my training loss, where I'm considering the square loss. I have a regression problem. I want to minimize this over all my parameter W. For a lot of predictor f of W, this will be a non-convex problem, okay? And this is always positive. And you see that if you find a predictor f of W, which is exactly fitting your data, this will be equal to 0. So you get a minimum. So for every f of W, which will fit your data, you will get a minimum of your training loss. So you have a lot of different minimizers. And so the question is that your algorithm, so today we will consider either gradient descent or stochastic gradient descent. So gradient descent, I am following the negative gradient direction to minimize my function. With stochastic gradient descent, I am not computing the full gradient, but I am only considering one random observation, IT, where IT is uniform between 1 and n. And so I'm following the negative gradient evaluated in one individual observation. And so what we will say is that this both algorithm will converge to some particular solution, and this is what we will call the implicit bias. Okay? So just to be very clear, what is the implicit bias? It is that my algorithm will minimize to some solution of this function, but it will not converge to a random solution. It will converge to a solution with a very specific property. Okay, and this specific property will be able to help us to understand why the solution of the algorithm will generalize well. Okay, so in that sense, really, like, the algorithm is responsible of the effective regularization, which is not directly prescribed in the optimization algorithm. Okay, and so when we are training large neural network, a large part of the regularization we are needed is coming from the algorithm we are using. So to understand the implicit bias of this algorithm will be really important in order to understand why SGD and GD is generalizing well when training neural network. So that's very important. And so now maybe the question, is how can you characterize this implicit bias? Because you could imagine a lot of different ways to do so. And so today we will really use what is called a minimal norm solution characterization. And so the kind of typical result we will show will be that if we are minimizing our square loss with our algorithm, GD, LGD, any algorithm you want, then we are converging to a minimum loss, okay, to a zero loss solution, which means that we are interpolating the data. So this we will have to, I mean, this will have to be proven, you know, because this objective is non-convex. But in addition of this, we are not converging to any solution. We are converging to a solution which is enjoying some very nice structure. And so what do we mean by a very nice structure? We mean that, in fact, the solution W infinity, the limit of your algorithm, will be the solution of optimization problem, which is a minimal norm solution. So R often will be a norm. So you are minimizing some criteria over your training, zero training error set. So the solution you find with your algorithm is the solution which will minimize your function R over all the solutions which are interpolating your data. And so we will often use this with a 2 norm or with a 1 norm. Okay. So this is how we will characterize the implicit bias in the talk. We will say that our solution is the interpolated solution with the smallest possible L2 norm or L1 norm. And then it will be possible, using this characterization, to infer some statistical property. So you know, for example, that if this will be the L1 norm and you have a sparse prior of your problem, then it's possible to statistically study the generalization property of the minimal L1 norm solution. So today we will not talk about generalization property. We will only characterize the property of the limiting solution, but this will help us to intuit, to infer some statistical behavior. Okay. And so you see that it really contrasts with explicit regularization, where you are directly modifying your optimization algorithm by adding some regularization. So today we will not consider additive regularization. We will just minimize our initial objective function with one particular algorithm, and this algorithm will find a particular solution with some good property. And so we will get the same effect as if we had in advance regularized the problem. And so this idea of implicit bias of optimization algorithm has been really studied a lot. So I tried to put some citation on this slide and on the talk, but I surely miss a lot. So if I forget to cite you, please, you know, really, I mean, I would like to apologize. And we have cited a lot of more people in the paper. And if we forget to cite you, just send me a mail and we will add, you know, a good citation. But what is important to have in mind is that implicit bias has been studied both for linear predictor, for neural network, for linear neural network, in the regression case, in the classification case. You have a lot of work. But in all these cases, also, for example, in one hidden layer neural network, I mean, you have a lot of works. But you know, the huge majority of all this work only concern gradient descent and not stochastic gradient descent. So today, what we are really trying to prove is like to prove some new result on the implicit bias of stochastic gradient descent. So now that we have defined what is the implicit bias and we have seen why it was important, you know, maybe a natural question could be, can you give me a simple example where you can, you know, show this phenomena of implicit bias? And so, as often in machine learning and in optimization, the simplest example will be the least squares. So I still want to minimize my quadratic loss for my regression problem, but now my model class will be the set of linear predictor. So I now want to minimize my mean square error, and this problem is convex. I have a convex problem, but I remind you that I am in the case where the dimension is really larger than the number of observations. So since n is smaller than d, I will have a lot of solution for this quadratic function. And so the question is to which solution I am converging. So in that case, you can easily show, so sorry, the slide is a little bit messy, but that gradient descent and stochastic gradient descent both will converge to the minimal L2 norm solution. So if you are minimizing this function with GD or SGD, your limit point will be the interpolator with the smallest L2 norm when you escape by the origin. Okay, so it will be the point the closest in the the Euclidean distance from your initialization. And it is really easy to see it. It's just by definition of your objective function, and that's something we will use later too. You see that your iterate, your gradient, is always in the span of your data. So the gradient, both the full batch gradient and the stochastic gradient, they are both in the span of the observation x1 to xn. So that means that when you look at the limit w infinity, it will be in the affine space of w0 plus something which is in the span of your observation, because at each step you are adding a gradient which is in the span of the x. Okay? So this is very simple. W infinity is in w0 plus something in my span of my observation, and I am doing some convex optimization, so I will find a minimizer of my loss. So also the loss in infinity will be equal to 0, and so that exactly means that your limiting solution is interpolating your data. And so what you see that these are exactly the KKT condition of this problem. Okay? Because what are the KKT condition of this problem? You are taking the derivative of this, so it will be W minus W0 is equal to some Lagrangian multiplier, lambda, times the derivative of your linear constraint, and the derivative of the linear constraint will be xi. So you see that the KKT solution of this problem is exactly that W infinity belongs to W0 plus an element of the span of the xi. And since you are converging to a 0 solution, then you are satisfied the constraint. Okay? So for in the case of linear predictor, it's not too difficult to see that the implicit bias of both gradient descent and stochastic gradient descent will be the minimal L2 solution. And you can generalize it to other algorithms, to gradient descent with momentum, and so and so. And so this is exactly what we can observe in these pictures, where you see in red here, I have the span of the xi. I will have here the orthogonal, and you see that this is all my level set of my function, which are orthogonal to the xi. This is a set where my loss is equal to 0. I start from some point W0, and you see the iterate of my gradient descent and of my stochastic gradient descent. And they will really converge to a point with a minimal L2 norm solution between W0 and W infinity. So that means like to the projection of this point on this line. This is what you can see in this simple example. So what have we seen? If we just do a small recap of the least square case, if I am minimizing my quadratic error with a linear prediction, then both the limiting solution of gradient descent and stochastic gradient descent will be my minimal L2 norm solution of my problem. And so you see that in this simple case, there is no difference between SGD and GD. So we are not happy, because what we want to prove is that SGD is generalizing better than GD, and in the convex case, it is not possible. So maybe what we can try to do is that we can try to minimize some other criteria than the L2 norm. Maybe we want to consider some other geometry, because we know that gradient descent is really related to the Euclidean geometry. And so maybe a good idea could be to consider the mirror descent algorithm. So I don't know if you are familiar with the mirror descent algorithm, but it is just a generalization of the gradient descent algorithm, but not under the Euclidean geometry, under a different geometry, which is described by the Bregman divergence of some convex potential psi. So given a function psi, you can really define the mirror descent algorithm as the following iteration. You are not anymore updating beta t, but you are updating your dual iterate gradient of psi beta t plus 1, which will be equal to your previous dual iterate gradient of psi beta t, and then you follow the gradient. So you have your primal space and you have your dual space, and you go from your primal space to your dual space using the gradient of your potential psi, and then you can map back from the dual space to the primal space using the gradient of the conjugate of psi. Okay, and what you are doing is that you are updating your gradient in the dual space, and then you project back in the primal space. So that's the mirror descent, and you see that if you are considering for psi the squared L2 norm, then you recover the gradient descent. So that's really a generalization of your gradient descent algorithm. And so then what is the implicit bias of the mirror descent algorithm? Then you can directly show that the solution will be the minimum, not of the L2 norm, but of your Bregman divergence between beta and beta 0. So you see that this is really an extension of the previous result, where you have replaced the L2 norm by the Bregman divergence, and where the Bregman divergence is really the way to define kind of a distance using your potential psi. And the proof is exactly the same. You are still using that gradient of psi of your limit will be in the affine space of gradient of psi beta 0 plus something in the span of your observation, and you are still using your KKT observation. The problem is that in that case too, you can show that still, if you are using stochastic mirror descent, it will be the same, and stochastic mirror descent will also have the same implicit bias than mirror descent. So in fact, what we will see is that in order to see some difference of a behavior between gradient descent and stochastic gradient descent, we really have to move to the non-convex world. We really have to move away from linear parametrization. And this is what we will do now by considering the case of two-layer diagonal linear network. So that's really this simple architecture, maybe one of the simple ones, where I will parameterize my linear predictor W by the component-wise product of two vectors U and V. So you can see that it is really equivalent to a linear neural network where each matrices are diagonal. That's the case of a diagonal linear network of two layers. And what I will do is that I will minimize my square loss for this problem. So even if the final model is still linear, if I consider W as still have a linear problem in W, so I am still learning the same class of function. Now with this parametrization, when I minimize over U and V, I have a non-convex problem. So this simple example has been studied a lot in previous work in order kind of to nicely understand what can happen when your objective function is non-convex, but still simple, and we can still do some nice computations. Okay, so I have a non-convex problem, so it will be harder to minimize, but at the end I am still learning a linear model. So the training is changed, but the exhaustivity is not changed. And so now the question will be, is it possible to characterize the implicit bias of gradient descent and of stochastic gradient descent for this simple model? So first, what we will consider is that we will consider an equivalent parametrization, which will be easier to deal with. So instead of considering W, which will be UV, and our prediction to be U component-wise multiplied by V, what we will do is that we will consider this little bit different parametrization. Beta will be W squared plus minus W squared minus. Okay? So there is a question. Okay, so that's a very good question, Indra. The question is the implicit bias independent of the training algorithm? Yes, that's very important, and that we will show today. Each algorithm has its own implicit bias. Sometimes it can be the same, but sometimes it can be different. But that's really a feature of your algorithm. Okay, it's not a feature of the, I mean, it's both a feature of your architecture and of your algorithm. Okay, so we are using this parametrization, and we will not consider the gradient descent algorithm, but we will consider is a small step size limit. So we will consider the gradient flow. So it is exactly the flow when the step size is going to 0, and I follow the negative gradient, both in the parameter W plus and in the parameter W1. And I will start from W plus is equal to W minus is equal to alpha, the vector 1. So I will be able to control the scale of the initialization. This will be very important, you will see. And so you see that when I go back in my function space, this initialization in W plus and W minus correspond to beta is equal to 0. So I start from my prediction to be 0. So let's try to see what is the implicit bias of the gradient flow for this problem. So let me remind you the problem. We are minimizing this non-convex function in W plus and W minus. How I am minimizing this function, I'm considering the deterministic gradient flow on my neurons W plus and W minus. And I start from an initialization of scale alpha. And what it is possible to show now is that your limiting solution will converge to a minimizer. Even if it's a non-convex problem, it's still possible to show that gradient descent will converge to a global minimizer of your training loss. In addition, it will not converge to any minimizer of your training loss, but it will converge to a very particular one, which corresponds to the interpolation solution minimizing some function phi characterized by your initialization scale. So you see, and this function phi, it's well defined. It is called the hyperbolic entropy, but the precise formula is not so important. What is very important is to see that depending on your initialization scale, you are not minimizing the same criteria. And even more important, if the initialization scale is going to infinity, so if you start from a very large initialization, this function phi will be close to the L2 norm. And if your initialization scale is going to 0, if you start close from 0, then your criteria will be close to the L1 norm. And so you see that with this non-convex parametrization of the problem, minimizing it using gradient descent and playing with the scale of your initialization, you will be able to interpolate between some L1 norm regularization type and some L2 norm regularization type. So if you start from a small initialization, you will be in what is called the rich regime, where you are minimizing some sparsity-inducing norm. And if you start from some very large initialization, you will be in what is called the kernel regime, and you will minimize some L2 type regularization norm. Okay? And so you see that if you have a model where you are assuming that your true solution W star is sparse, you will be happy to minimize the L1 norm because it will lead you to some good statistical property. And then you could say, but why are you not taking directly alpha equal to 0? It's because the point W plus W minus equal to 0 is a saddle point for this problem. So if you start from 0, you will stay in 0. And you also observe that the closer you start from 0, the slower it will be to escape the saddle point. So you directly see kind of that you have a trade-off between the optimization property and the statistical property of your problem. If you start from a small initialization, you will have some good statistical property, but you will have some slow convergence of your training loss. So that was, for the gradient flow algorithm, for the deterministic algorithm, and this is very clear. And this has been done by Gunasekar and Lee and other people, and Nati in this very nice paper at Colt in 2020. And so now the idea is really, can we analyze this for stochastic gradient descent? And this is what we will do in the end of the talk. But so first, how can we, prove and understand this result? It will really be based on this mirror descent proof we have seen so far, is that in fact, when I am considering a gradient flow of my neurons W plus and W minus, I can also try to look at what does it mean for my beta. Okay, what is the induced dynamic of my beta, which are equal to W squared minus W squared minus. So I am doing a gradient flow on W plus W minus. What is the induced dynamic on beta? And it is possible to show that in fact beta will follow a mirror descent. And it will follow a mirror descent whose potential is given by my hyperbolic entropy characterized by my initialization alpha. So you see that you can either consider that you are doing a gradient flow on your neurons, but when you look in the space of your function, in your space of beta, in fact, you are doing a continuous mirror descent whose potential is given by the entropic regularization. Okay? And so this directly gives you the result because we saw that the implicit bias of mirror descent was given by your potential. And so we directly recover that the limit of beta will minimize phi alpha of beta over the beta which are interpolating the solution. Okay? So the proof is really easy using this mirror descent interpretation. It has been proven by Guy, Hazan, and Singer in this very nice paper at ALT in 2020. So let's now try to do the same for stochastic gradient descent. Okay, but even before, a quick recap. So when we are minimizing our quadratic loss with our diagonal linear network, we are using a gradient flow. We have a hidden mirror descent interpretation, and we have these two different behavior. If we have a big initialization, we are minimizing something which is close to the L2 norm. And if we have a very small initialization, we are minimizing something which is close to the L1 norm. And so you see in the space of the function for big initialization, we have something which is very close to the Euclidean geometry, whereas for small initialization, we recover something which is closer to the L1 geometry. Okay, so now the question is, can we get the same result for stochastic gradient descent? And that's really the main topic of our paper. So let's recall what is the setting. We want to minimize the square loss with this parametrization, so which correspond to a diagonal linear network. But no, we are not considering gradient descent, we are considering stochastic gradient descent. So at each step, I am considering the gradient in only one observation, not on all the observations. And so the question we want to ask in the last 15 minutes, 10 minutes of the talk is, will we get the same implicit regularization or will it be modified? And can we also use the same underlying mirror descent structure? So first, let's see empirically what we can see. So if I look at the generalization property, so if I look, I'm just doing, okay, a simple problem. simple sparse regression problem where beta star will be sparse and I want to recover it. And I compare gradient descent and two different runs of stochastic gradient descent, where the different run will correspond to different order where you are seeing your data. And what you can observe is that first, SGD will always have better generalization property. And you are also observing that the different run of SGD will have different generalization property. And then what is kind of interesting is that you see directly that it is inversely correlated to the convergence of the loss. The loss of the run in blue is converging at a slower rate than the loss in yellow. And then you see that you get a better generalization property. This is what we will try to recover. But first, as I gradient descent, we had to go to the gradient flow. So we will have to do the same in the stochastic world. And also the first important question is, how is it possible to define a stochastic gradient flow? So we have the stochastic algorithm. And then the question is, what is the best continuous version? What is the best dynamic in order to model this discrete algorithm? And so as often we will consider a SDE. So it is like a gradient flow perturbed by some Brownian motion. How should we model the covariance of your Brownian? And to do that properly, it has been investigated recently in a series of papers by Vostovovic. And what is very important is to look at what is the initial covariance of your noise in SGD. And what you want to maintain is two important properties of the covariance of the noise. You want to have a noise which will be still in the span of W plus W minus component-wise multiply with your observation. That's the first feature. And the second feature is that you want to maintain the same covariance. Okay. So when you want to model your discrete algorithm with a continuous dynamic, we will try to pick a covariance sigma such that these two important properties are preserved. We still want that the noise belong to the span of W component-wise multiply with your observation. And we want to keep the same covariance matrix. So this is very well explained in the paper. But what you can show is that if you are taking this modelization, you will maintain these two properties. So we really have our deterministic gradient flow perturbed by some Brownian motion with one very particular covariance matrix. And this would be very important. And let me remind you that this is only a model. This is only an approximation of stochastic gradient descent. But what you can see is that empirically, if you are doing some run, the stochastic gradient descent and the stochastic dynamics are really behaving in the same way. So even if this is only a model, this is empirically describing quite well the performance of stochastic gradient descent. And it is possible to show some approximation result to show that the distance between the SDE and SGD is not too far away. So what is the main result we can prove in the paper is that with some probability P under some initialization alpha 1 and under a condition on your step size where your step size has to be smaller than something which depends on your probability on the largest eigenvalue of your covariance as usual in optimization, but also depending on your initialization scale alpha and the norm of the smallest L1 norm interpolator. So under this condition on your step size, we can show two different results. One, it is possible to show that in fact, your stochastic flow will converge your dynamic is noisy, you will converge to a solution of your problem. And the second thing we can show, which is the most important, is that this limiting solution will be a solution of a minimal norm problem, where we are recovering, we still have our hyperbolic entropy, but now it's not anymore described. It's described by alpha infinite, and alpha effective, which is equal to your original alpha times a number which will be always smaller than 1. So let's try to analyze it a little bit more. So for the gradient flow, what we had, it was that the solution of the gradient flow was the minimal hyperbolic entropy solution, where the hyperbolic entropy was described by your initialization scale alpha. Now, what we can show for the stochastic gradient flow is that we get an alpha effective, which is always smaller than the alpha you will get with the gradient flow. And how much smaller it is, it really depends on the integral of your loss. So that's really what is important. This will be stochastics. So that's why you see that for different runs, you will have different implicit bias. But the largest the integral of the loss is, that means that the slower you are converging, the better your implicit bias will be, because alpha will be smaller. Okay, so this really shows you that the stochasticity of SGD is helping you to get a better implicit bias, because you will be able to characterize the implicit bias with the entropic with this function, but not in alpha, but in an alpha effective, which is strictly smaller than alpha. And if you are asking, what do we mean by strictly smaller, and if it's possible to be a little bit more quantitative, this is what we can show, is that if your initialization scale alpha is going to infinity, you will have no benefit, and SGD and GD will behave exactly the same. Okay, so alpha effective, alpha infinity will go to alpha. But when alpha is small, it will be possible to show that the alpha effective will really be an order smaller, where zeta is some constant which will depend on the problem, but zeta will be strictly positive. Okay, so you show, it's possible to show that really the dependence in alpha of alpha effective in alpha will be better. And this result is requiring some additional assumption on the boundness of the iterate, but which are kind of technical. So we always have that the alpha effective is smaller than the alpha, and under additional assumption, we can show this result. So let's just finish with some empirical result, and then we will go to some question. Oh, there is one question. So the question is, the stochastic gradient flow converges to an interpolation solution, but normally is not min-norm solution under different initialization. So maybe it was not clear. Your limit will always converge to the minimization of this problem. Okay. Then this function phi will be described by alpha. And when alpha is small, this will be close to the L1 norm. And when alpha is large, this will be close to the L2 norm. But for every initialization, your solution is corresponding to the minimization problem of this, to the solution of this minimization problem. So let's see just some experiment to finish. So we really see that if I look at my generalization property with respect to alpha, then the stochastic gradient descent has some better generalization property. This is also can be seen here, okay, where you see that SGD is below. And in fact, this is what is important, this is what we show, is that it's kind of equivalent to do stochastic gradient descent from alpha or to do gradient descent from your alpha effective. Okay, we can talk about it during the question. And then we really have this idea about like the connection between the alpha effective and the integral of the loss. If we consider these two runs, we see that for the blue run, the loss is converging at a slower rate, which means that the integral of the loss will be larger, and we recover that the generalization property will be better. And just to finish on this, how is the proof working? Is that in fact it is still possible that for the stochastic gradient flow, we have a hidden mirror descent structure. But the difference now is that my potential of my mirror descent will be time dependent and will be stochastics. So that's like the key technical difficulty and technical novelty of the proof kind of is that I have a mirror descent with a stochastic time varying potential. This is what is very important. The fact that I am adding some noise will be less important because my noise I am adding is still in the span of my observation. But so you can see that with this structure, you can directly obtain our result using the KKT solution. What is really hard to get is to show the convergence of the iterate with high probability to an interpolating solution, and then to control the quantity to show that the integral of the loss is converging. That's the two difficult parts of the proof. And if you are interested in them, you can look in the paper. So you can also show some result about the label noise, but we won't talk about it now. So just to conclude, what are the two take-home messages of the talk is that using some appropriate continuous modelization of gradient descent can help you to get some very interesting and pertinent results. And then for a very specific type problem, so namely diagonal network, 2 layers diagonal network, it's possible to show that the noise in the stochastic gradient descent algorithm can probably help you to recover some solution which will have better generalizing property than if you were only using gradient descent. So what are the next steps? Then we are actually working on to extend this result to the classification case, and then it will be interesting to go a little bit beyond the simple case of a diagonal 2-layer diagonal neural network and to go to more sophisticated architecture. Okay, many thanks. So that's all for me for today. So I don't know if you have some questions. I'm happy to take them now.
Yeah, okay. Hi, Nicolas. Thank you very much for your great talk. Yeah, so I will handle this QA session instead of Taj. So I'm surprised by this result. So let's move on to the QA. So first, I have a question. Okay. So first, this is just a confirmation. So this setting implies a variance reduction of the method because of the interpolation, right? So that means that.
So you mean why do you converge to an interpolation?
Yeah, and the variance reduction happens so to accelerate the convergence speed. So that is noise term will vanish as the optimization proceeds. So,
yeah, so if I understand well your question, tell me if I'm wrong. You say that for you it's kind of weird that you are converging to a solution whereas you are using stochastic gradient descent with a constant step size.
Yeah, and the noise term
that is because
will vanish.
Yeah, so that is because we have a system with no statistical noise. So if I'm looking at my system, it exists a beta star such that yi will be exactly equal to beta star times xi. So that's, you know, that's the setting of SGD, so you have no noise at the optimum. And so in that case, it's possible to show that SGD with constant step size will converge to the solution.
Yeah,
because you have no noise at the optimum.
Thank you.
So there is no use to use variance reduction.
Yeah, makes sense. So on the other hand, so this study clarifies that noise is key to control the implicit bias. So from these two observations, does it mean that the noise is important especially in the beginning phase of training?
That's a good question. So you say that is it that the noise is more important at the beginning or at the end? I'm not sure to have an answer. You know, it could be interesting to, for example, you know, what is happening if you start with SGD and then you go back to, yeah, so in some sense, it will, okay, this is exactly what we are doing with the label noise. And so noise can be important at the beginning because you want to slow down your convergence. So if we look just quickly at the result with the label noise, so you are just doing the same setting, but you're adding some noise on the label. And so that means that kind of you can, you know, you can have a, I mean, you're adding some noise, so you are slowing the convergence. And so you will get a larger integral of the loss. And so what you will observe is that by slowing down the convergence and by increasing the diagonal of the loss, you will get a better implicit bias. Okay, so you could say that the noise at the beginning maybe will slow more. Yeah, so the noise at the beginning will be more important because the scale of the noise will be proportional to your distance to the solution. And so since it will be more important, it will slow more the convergence. And so it will be more important in the implicit bias aspect.
Yeah,
so yeah, I think you're right. I think that the noise at the beginning is more important.
Yeah, makes sense. So very interesting. So we have received some questions in the chat window. So can you see them?
Yeah, so hi Lenaik, so thanks. So is it possible to compare the speed of convergence of gradient descent initialized with alpha infinity and stochastic gradient descent with initialized with alpha? No, so we don't have precise rate of convergence. So for now, what we know, you see that empirically they have the same rate of convergence if you compare the red and the blue curve. It's possible to show that the rate of gradient descent with alpha infinity will be linear with a contraction which will depend on alpha infinity. But we don't have such result for a stochastic gradient descent now. But empirically, you see that they have the same rate, but it is not proven. And then we have a second question by someone anonymous. Is that correct that Adam is an extended type of SGD? Yeah, I mean, that's correct if you want. I mean, Adam is a different algorithm which kind of implement two kind of correction of SGD. You are using like adaptative step size and also like adaptative momentum. And so then the question is, are there any criteria to adopt suitable optimizer? But you could say that implicit bias is such a criteria. I mean, if you are able to study the implicit bias of all your optimizers, then you could use the optimizer whose implicit bias will correspond, will be nice for the problem you are considering. So if you want to have some L2 regularization property, then you can use an optimizer with implicit bias connected to L2. And if you want to have some L1 regularization properties, then you should use algorithm with an implicit bias related to L1 property. Is there any other questions?
So I have one, if I may. So in
Volker,
terms
sure.
of the SGD, we benefit from this implicit regularization. But you know, we set up the problem, we write down the optimization, we choose the optimizers. Why not just put a bit of explicit bias and run gradient descent? Have you guys compared if anything happens to gradient descent with a bit of Tikhonov regularization? Does it also start to get near what SGD does?
So you mean that what will happen if you add on top regularization?
Yeah, some explicit regularization, because remember, we are setting up the problem.
If you are adding explicit regularization which correspond to the implicit bias of your algorithm, then you will observe the same performance for SGD and GD. because the the explicit one will be stronger than the implicit one, kind of. So that's a very good comment, like why, if you, at the end what you want to do is to solve a sparse regression problem, why are you doing this, and why you are not using the lasso directly, adding some L1 regularization, and you will get your optimal solution. So I think that a way to see it is more, trying to, it's like a starting point to try to understand why GD or SGD are efficient without regularization for some problem.
Mm-hmm. Thank you.
But you're totally right that if your initial problem is to solve these sparse problems, then you should rather directly add some explicit regularization.
I mean, what is interesting is that the adaptive algorithms have different kinds of biases as well. Somehow within your framework, you should be able to also see whether or not what kind of, let's say, mirror map they use or what kind of implicit regularization they do. So that's actually an interesting, so the tools you have might be relevant also there, like seeing what AdaGrad does, for example, But that's yet another research question.
Directions.
Thank you for the talk. Yeah.
Thanks so much for the invitation.
So I have a small question, okay?
Yeah, sure.
So I'm wondering what is the key of this problem setting to produce this amazing result, and when this can be extended to other problem settings. Do you have any intuition?
Sorry, can you repeat your question? I did not.
So I'm wondering what's the key of this problem to show this amazing result. So, and when this can be extended to the other problem settings. So is there any idea?
So I say, I think the key is really this mirror descent.
So dynamics of the mirror descent is
mirror
key.
Descent structure.
Yeah.
And the fact that for this problem, the potential now is, it's changing thanks to the noise. This is what is key.
Yeah.
And so this is kind of important to have in mind. It's just like, if you were directly using mirror descent and you were just adding some noise to your mirror descent, so in some sense, if you were just, considering any noise, then you will have this, but you won't have this, and you won't get a better implicit bias. So what is very important is that we are adding the noise in a such way that when we look in the function space, the implicit bias, the geometry of the implicit bias is modified by the stochasticity. So in some sense, the stochasticity of your problem is modifying your geometry of the flow, and in a time-dependent manner. So that's really what is key.
Yes, thank you.
When you have this, then the proof is kind of done. Then you have, some technical subtleties, but this is this, time-dependent stochastic mirror descent structure, which is key.
Yeah,
so that's why, for example, to extend it to classification, that's what we try to recover. Is it possible to have this mirror descent view for the classification problem, for example?
Yeah, interesting.
So for me, this is what is key.
Yeah, thank you very much. So, so I think so. Is there any other questions? Okay. If nothing, so let me close this session. Okay.
Thank you so much.
Yeah, perfect.
I hope to see you soon, all at EPFL and then later in Japan.
Yeah, thank you very much, Nicolas. So this talk was very informative and surprising. So, okay, so I think it's time to close these QA sessions. Thank you very much again. And thanks everyone for raising several questions. Yeah.